Welcome to my video tutorial on pH and pK of weak acids from titration. In the last video tutorial, we looked at how we could work out pH from titrations. For example, what would the pH be if 26 centimetres cubed of 1 molar HCl was titrated with 25 centimetres cubed of 0.1 molar NaOH solution? Notice that my examples use strong acids and bases. These sort of titrations would be carried out with a suitable indicator, for instance phenolphthalein, and there'd be a colour change once neutralisation had occurred. We'll often refer to this as the end point. In an ideal world, this end point would occur when the two solutions, such as HCl and NaOH, were mixed in exact equation proportions, or we could say stoichiometric proportions, and this is known as the equivalence point. It can sometimes be referred to as the stoichiometric point. Realistically, the equivalence point isn't necessarily the same as the end point because during the titration salts are formed and these may have an effect on the pH of the mixture. However, the equivalence point is not always pH 7. We will be using the equivalence point to work out the pH and pK of a weak acid from titration. Before we begin, let's have a look at a typical titration curve for a strong acid-base titration. Now, these sort of titrations will be carried out using a pH probe rather than an indicator. At the start of the titration, the pH will be low, as the only thing in there is a strong acid. So let's just say we started off with 25 centimetres cubed of acid. The titration, as it goes on, will start to rise slowly. Then there will be a rapid rise in pH. Then, as the base is in excess, it will start to rise again gently. This steep portion of the graph is known as the equivalence point, and if you continue the vertical line down towards the x-axis, this tells you the value of the volume of base, in this case, that was needed for neutralisation. For this titration between sodium hydroxide and hydrochloric acid, the pH stoichiometrically at equivalence should be at around pH 7, but this isn't always the case. Can you sketch out what you think a 25 centimetre cubed volume of weak acid titrated with a strong base such as sodium hydroxide, what the pH curve would look like? As a hint, think about the pHs at the start and then at the end, then have a go at filling in the pH changes as the volume of the strong base increases. You could use the same axes as before. Pause the video for a minute and then come back in a moment to see if it's the same. Okay, I started with 25 centimetres cubed of weak acid and my equivalence point is about 25 again. However, the starting pH is higher this time, and that's because we've got a weaker acid to start with. We can see that the pH at equivalence this time is greater than that for a strong acid, strong base. This is because at equivalence all of the weak acid is neutralised and converted into its conjugate base. So at equivalence the resulting solution is slightly basic. Then as the excess strong base is added, the pH gradually rises again. We will have a look at pH curves for different acid-base titrations in my next video, and we'll have a look how different indicators are selected due to this difference in the endpoint pHs. For now though, let's have a think about what's just happened in this titration. We're going to call the weak acid HA and the strong base is sodium hydroxide. We would pipette a volume, usually 25 centimetres cubed of HA, into the flask and then add the sodium hydroxide from a burette with a pH meter in the flask. During the titration, the weak acid in the flask would get used up and it would get turned into a salt. And of course, in a neutralisation reaction, water is also formed. Now, to start off with, at the start of the titration, there'd be lots of the weak acid and hardly any of the salt. But the concentration of the weak acid would fall continuously and the concentration of the salt would rise. Exactly halfway through the titration, exactly half of the weak acid will have changed into the salt, and so the two concentrations would be equal. So at halfway we could say that the concentration of the weak acid is equal to the concentration of the salt. If we were to look at the expression for Ka, we know from previous that the expression can be shown as I've put here. Now we know that Ha is a weak acid, and weak acids only partially dissociate, so very few of these ions are going to be produced. So what we can assume is that virtually all of these basic ions are actually coming from the salt. So therefore we can actually say that the concentration of the basic ions is equal to the concentration of the salt. So putting this into the expression for Ka, we can rewrite it as shown. Now, because the concentrations of the salt and the concentration of the weak acid are equal halfway through the titration, we can actually simplify this expression further. And if halfway through equivalence, if the Ka is equal to the concentration of the hydrogen ion, then pKa is equal to pH. So what does this mean? Well, in a weak acid, in a strong base titration, at half equivalence, so that would be V/2, the pH at this point would be equal to pKa. Now, exams can often ask you to use graphical data to work out pKa. So all you need to do is, and if it's for a weak acid, you need to find the equivalence point, half that volume, and then whatever the pH is at that point will equal the pKa. Of course, you may also be asked to calculate the Ka from pKa, in which case you just have to do the antilog of that value, which is shown in my previous videos. So now to test your skills, have a go at plotting the following data to work out the pK for ethanoic acid. And I'll see you for my next video. Thank you. Bye.